Students, myself Javi and Dr. Kiran Yadav. In this session, I will discuss about the various phenomena which were not explained fully by the classical mechanics, and some new theory, or I can say quantum mechanics, was needed for their explanation. At the beginning of 20th century, there were several experiments or behaviors such as the ultraviolet catastrophe, the Stern-Gerlach experiment, and the hydrogen atoms. These experiments or these phenomena could not be explained by the classical mechanics, or the classical mechanics was not capable of explaining them. According to classical physics, it was basically developed after the Newton's work in a book called and it is basically given by Newton's laws of motion, which successfully explains the motion of objects and planets. Classical physics is basically based on the kinetic energy and potential energy of the particles. Here in the equation, a Hamiltonian of a system is written, which is sum of the kinetic energy and potential energy of a particle. Here the term Pi by 2 mi is the kinetic energy and U is the potential energy of the particle. In the end of 19th century, experimental evidences accumulated showing that classical mechanics failed when applied to very small particles. So there were several other phenomena as well which were not explained by classical physics. One such phenomena is black body radiation. Black body radiations are when a hot object emits light. At higher temperature, the radiations become of shorter wavelength. An object capable of emitting and absorbing all frequencies uniformly is known as black body. The experimental observation: as the temperature raised, the peak in the energy output shifts to shorter wavelengths. There were two laws given. First one is the Wien's displacement law. The statement of Wien's displacement law is this one: T lambda max is equals to C2 upon 5, where C2 is a constant whose value is 1.44 centimeter Kelvin, and Stephen's Boltzmann law, according to which E is equals to 8 T is to power 4, or I can write M is equals to sigma T is to power 4. So then there was first attempt to describe energy distribution of black body, which was done by Lord Rayleigh and Jeans, and popularly known as Rayleigh-Jeans law. This used classical mechanics and equipartition principle to describe the energy distribution. The result of this was rho is equals to 8 pi kT upon lambda 4. This law was although successful at high wavelength, but it fails badly at low wavelength. Okay. So then came Planck's distribution in picture, which explained the spectrum of black body at higher as well as lower wavelength. So in case of Rayleigh-Jeans or Wien's displacement law, each assumed the energy to be continuous. So Planck gave a new hypothesis. He considered the energies are discrete. He considered energy to be quantized, means energy can have only certain values and these values are given by the formula E is equals to NH nu, where H is Planck's constant, nu is frequency, and N is an integer whose values can be 0, 1, 2. Then he gave a Planck's distribution law, which is rho is equals to 8 pi hc divided by lambda is to power 5 is to power hc upon lambda kt minus 1. At higher frequencies, this Planck's distribution law is quite similar to Rayleigh-Jeans law. And the Planck's distribution law also follows Stefan Boltzmann law. So the Planck's distribution law successfully explained the blackbody radiation curve at both high and low wavelengths. So the assumption that Planck made that energy is quantized seemed to be of great importance at the time, and this assumption led to the foundation of quantum mechanics. So this is all for this session. Thank you.